All right, it looks like we're back. Or it looks like we're live, not back. Anyway, hello everyone and welcome back. This is Sentient Cloud. Now, it has been quite some time since I've streamed. There's reasons for that I won't get into, but yeah, just trying to get back into the swing of things a bit. And yeah, so I'm going to be doing some programming for maybe an hour, and then I'll probably do some gaming. I found a new Factorio kind of mod pack overhaul sort of thing. And so I'll probably be playing that, and yeah, so we'll see where things go. Now, as you can see by the title and the description, I've once again gotten sidetracked and sucked into writing my own programming language because I want to. And I keep failing to. So I want to more. So, with all that said, let's get into it. I'm going to make some changes here. So first thing I need to do is I need to go and change this because calling this a program is a little bit not, that's just not true. So it's a syntax tree. I'm not going to say abstract syntax tree because that just takes forever to write. So I'm just going to call it a syntax tree. I suppose I could call it an AST, but it's not exactly obvious from that what it is. And actually, I don't even think this is technically... Is it an abstract syntax tree, or is it just a syntax tree? I'll figure that out. Anywho. Let's see. Actually, this isn't really necessary. These two, at least. Because the syntax tree is going to be produced using parse, so we'll just go ahead. We'll think here. I guess we'll just call this tree delete. Let's do tree print. A few minor changes here. And we'll just go ahead and pass the pointer. And there's going to be no changes, so we'll just call it const. And actually, I don't... Let's see. I think const pointer refers specifically to not changing or replacing the pointer. So I think I could be wrong, but I think that it's okay to call that a constant pointer. Let me go to the parser here. A lot of this stuff is going to have to be changed because I'm thinking of things differently. Okay, so don't think, do I need to return anything really? I don't think I need to return an error code for this. I don't think that's necessary. All right, so we'll do void parse. It is going to take the syntax tree and a lexer. I suppose I could also... Do I want to have the parser make the lexer, or do I want to make the lexer ahead of time and then send it to the parser? I don't think there's anything wrong with you sending or creating the lexer in the parser. So then I would just need const name. It's going to be here. Okay. So we need to create a lexer. Let's make sure this is 0. And I'm using C for this. I don't recall what the let's split here real quick. I don't recall what the version of C that this is using. It's using GNU 17. That's fine. That should be fine. And everything else here, I think is okay. In this case, I'm not using my little build tool because that works only for C++. But I've already got a file here, so this should be fine. Okay, let's close that. Okay. So this can replace. This can be replaced with tree delete. That's tree. Pretty sure. So this should be good. Okay. And actually, so it needs to be a couple of things here. So first, I'm going to go ahead and put in an assert, and this is just going to check that tree is not null. Let's be non-null. And I'm also going to, not going to assert that, but tree nodes. Because I don't want it to crash because it's trying to access those. And so in that case, this can just be gotten rid of because it's already going to break. Here, go ahead and include assert. Cool. Okay, and this goes. Well, actually, I'll leave that there for the moment. Fix that later. Okay. Okay, let's replace all these. And actually, since I'm here already, I'm going to go ahead and test this out real quick. So I think if I do that, okay, so that's not actually showing if there's an error there. So I'm going to have to test this. That's okay. We'll do that. All right. So for zero. Is that? I think that's all that it's going to need. Oh, shoot. Do that. All right, cool. That's pretty easy. Okay. Okay. So parse is going to need to have roughly the same thing. So just going to read. And we're essentially just copying all this. So I'm just going to go okay. Where that? Okay, so this is, so we're reading the buffer. I guess this does need to be able to return an error code just so that I can know if the file actually opened successfully. Okay. And like, you know, basic stuff like allocations, but I guess that also applies to all of the parser elements because it's not going to report parse errors in that respect, in that way, because I want it to produce an entire syntax tree. But it's going to report like problems like not being able to allocate, things like that. Okay. should be fine. Okay. I think that's going to work fine. Okay. This is not. I'm going to have that in there. Okay. I don't know why that would be an I/O error. It's a little weird. I'm just having to go back and decipher all of this stuff and make sure I did things the right way to begin with. Here, go ahead and delete this and into parse. It's going to take some extra. No, doesn't take Luxor. Okay. Cool. All right. Anything else here should be fine. One thing I do want to try is adding in parse func. Because one of the things I want to kind of accelerate the move to the sort of evaluation step, and so I want to be able to actually produce a like a compilable C file with this, because it's going to be translating at least initially into C, transpiling into C. Okay, so we're starting with that. We'll go here into func, parse func. And I'm gonna go ahead, because none of these are going to be called in this particular file. So we're going to get rid of that, put these all up top. And down. Okay, cool. Nice. I think I want to do fix them with static. Not sure about that one. Oh. Cool. All right. And parse func needs to be up there too. All right. Cool. Okay. This can go, because that's not going to matter. That shouldn't return an error. That's not an error. That's just a success. Right, if we're trying to parse an expression and it manages to reach end of file, that's perfectly acceptable. It's not acceptable if we reach end of file while we're still trying to parse a string or something like that. But in this case, this is perfectly acceptable. Okay. All right, so we'll go here, and I want to put up. Oh, no. Let's go here. Okay. There. Cool. Let's go all the way down. Okay. There does not appear to be. Okay, it's if expression. I don't know why. It's called if deck. Func. Just name that. All right, now I have a bunch of different nodes here. We're going to have func ID, or I guess we'll do name, not ID. Name operen as an open parenthesis, close paren. What else? Return. That one's optional, but it's likely going to be there. So if it's not, if it doesn't exist, then we'll just call it like a void, because it's going to be, well, if it's not there, then it's not there. It's just going to be nothing. Okay. And then O brace, C brace. So those are all that are like basically guaranteed to be there. And then we're going to need parameters. And we're going to need function body. But those are different. Those are not going to be required straight away. Okay. So now, and we can even call this funcsim, right? That makes sense. Okay. So here, we're going to go ahead and try to parse that. So we're going to funcdef. And make sure to check for null. So let's do funcdef sim is going to equal lexer node. So that's the first one. We already know that it's a func type, so that's fine. Then we'll go ahead and advance the lexer. And then actually, what does advance actually do? Don't know if I necessarily want to do that. Yeah, let's stick with this for now. Okay, so start here. So if lexer node type does not equal PID, turn I don't know if I actually want to return here. What I'll do is funcdef name equals, so we're going to make this a node. I need to do that there. This is going to see, it's kind of tough to decide if I want this to skip over it or just insert an error and then move on. think insert an error and move on is probably the correct way to go. So like basically, if you forget to put in a name, so like let's take an example here. Let's say we do func, and I'm not positive if that's the correct sim, but we'll just go with that. So func, and then we start working on writing out our function. We do blah blah blah. I think I want to make sure that it says here, you know, oh, you need to insert a name, and then it'll just move on and continue checking. I think that'll be more accurate. Maybe. We'll see. Okay. So if that's not ID, then this is going to be it's going to be an error type. Do I have NT error? I do. Okay. So node type error. And node type error needs let's see, start and end are going to be insert node start xer end, not end, excuse me, start. We want it to make sure that it just says, you know, hey, that's not in the right place. You need to put that in the correct place. Okay, and then value, I think I need to make an error message here. So let's go to the bottom here. It's going to have message and also so actually I don't even necessarily need that. I just have a regular null terminated message. We'll just do that. That's easier. That's much easier. Okay. And that needs to be okay. So let's do enter. I suppose I could actually just have like a list of error messages that are always like globally known. Maybe. Yeah, maybe this will work. Well, this is a great idea, but I'm going to try it just to save myself some allocation. Okay, so we need, what is that? First one would be, we'll just call it missing identifier. Missing identifier. Okay. Okay, cool. And else, it's going to, and so the other way around. So if it does equal this, then just set it equal, otherwise do this. lex to advance the lexer. Oh, I don't need this. There we go. Okay, cool. So that's the first step. That's getting me the identifier, or it's returning an error. But this is not happy. Why are you unhappy? Hold on. That's why. No, that's not why. Okay. Let's go through here. So it's going to be dot type. What's that? I'm just going to use this little thing. Start that. And that. Values. Okay, why are you unhappy? Why are you? Ew. So how do I make that happen? Okay, well, I'll just go and do this then. Now, if I go ahead and I think I can save space because I don't think this is needed. Just that. Cool. Okay. Sure, return success. So this works. Okay. So next is getting the open and close parentheses. Actually, let's hold off on that. Let me go to .c. I want to make sure that we're printing these correctly. Gee whiz, that's a lot. Okay, here we go. Here, case t func, which is not. Oh, that's not defined. Make sure it's t. Okay. Basically copy all this. Okay, so then here, do print. I'm just going to go ahead and do. Delete. Just want to make sure that this also gets delete. I don't think either of those, well, actually, identifier one maybe needs to be deleted. Funcsim doesn't need to be deleted, technically speaking, because it doesn't actually end up doing anything. ID doesn't delete, like deleting ID does basically nothing also. So really it's just free node value. There's nothing in there just yet is going to require extra steps to take care of. For something like this, for a binary expression, that is necessary. Like theoretically, because you might have a case where you've got a string that needs to be freed. Doesn't need to happen for the operator though, so that saves some effort. And then same for like that. So that means I don't want to try and do something with that. Yeah, we'll leave those as is. Okay. I think I want to actually call mem set for everything anyway. So node set, yeah, 0 size of node. Just to be safe. Is that going to be a heavy? Yeah, it is. Okay, well, whatever. Okay, let's test this out. Let's see if we can get this to do the things. We open up this. This is going to be replaced right now with func main. Go ahead and check just to make sure that I'm not making a very big mistake. Okay, yeah, so that is the correct keyword. Right, because it's not actually being set to that, so that's why. Hold on. Sure. Gotta make sure to actually set the type of that to and then yeah, value set there. Actually, you know what? Save myself some trouble. Send to func def. What is this going to be? This can be. That's not really going to save much trouble, actually. Start. Sim start. And then end. It's going to be. In this case, it's going to be the name. So name end. So that should work. And every node is going to basically be, it's going to include the size of the constituent nodes. So Okay. So that should work. Okay, yeah, so it passes. Func_def, yep. Start and end is all okay. That is in fact not the correct. Okay, yeah. Start and end are not correct. That is just wrong. So why is it wrong? That's something to do with the Lexer, certainly. So we now need to go back, check out the Lexer, make sure that we're getting correct numbers. Hmm. Okay, so that's in Lex ID. I think I might have an idea of what's going on. Hold on. I should have. Yep, that's why. Okay. These are the wrong way around. Hold on. That's the wrong way around. Hold on. Okay. There we go. Perfect. Well, is that actually perfect? There should be a space there. So, that's white space. So, I think that's correct. Maybe. Hold on. How is it printing? ID. Okay, yeah, so func is being printed that way. Where is ID coming from? Okay, so it is indeed getting starting from the string value. I realize this is a minor thing. It's not a huge issue, but we want to make sure that this works properly. So, okay. So that's index of 0, 1, 2, 3, 4. Yeah, so something's not quite right here. So let's go to Lexer again. Okay. Do one space. Oh. Yeah. Skip white space is going there. Is there anywhere else where skip white space is occurring? What is it? I think it's G skip white space. Just 2 places. Okay, that's fine. So that should fix it. There we go. Okay, that is what we want. Okay, cool. Perfect. Perfect. Okay. Now we're about 45 minutes in and making decent-ish progress. Man. All right. So let's go ahead and we'll go ahead and finish this part up. Just like the basic declaration of a function, and then that'll probably be 15 minutes, and then I'll be able to go, or be able to. That's wrong framing. Anyway, doesn't matter. Okay, so we've jumped ahead. So, all right, if answer type oh, what's it? L. Oh, okay. Yeah, that's fine. L paren, O paren. Either way, it doesn't matter. That's good. That is what we want. Otherwise, yeah. I'm going to rename those to. There we go. Just going to rename this to L paren. And then L brace. Oh. Pressing the wrong button repeatedly. Okay. So L paren to be basically the same idea. Should probably put something in that's a little bit more clear, like, you know, an enum that lists through error messages, like for types. But error expected yeah, we'll work with this. It's not ideal. Let's go with that. Okay. Advance the lexer. That's going to essentially be the same thing for other. Now, inside here, normally I would be checking for parameters. In this case, I'm not going to do that because that's it's going to require a lot more work to get that set up. So I'll just save myself the trouble for the moment and just work with what we got. So start right here to there we go. Okay. Okay. test for that there. We'll test for that in the node print function. So case t error printf that here. Checking for actual errors. Okay, so go to, where are you? There we go. Okay, so it's going to call node print on. Jeez. Do that. Save myself some trouble. So we want to call it on lparen. And that should be good. And now it prints error. Nice. Cool. Now this stuff is going to have to be also dealt with in the evaluation, or I guess optimization step. But yeah, cool. I guess I could also just make it so that if it discovers there's an error in one of these, it'll automatically set result to an error code and then just exit. It'd be faster. No reason to try to evaluate it if there's an error in this. But anyway, okay. Cool. So let's see, got another 10 minutes. Okay, now let's see. You know what? Actually, I'm just gonna go ahead and stop here. Finish parsing. I'm gonna go ahead. I'm gonna move to the evaluator. The optimization step is kind of, technically speaking, it's optional. And I kind of want to play around a little bit with this. So endf now.8 underscore h, I can say. Header guards. Okay, now there's going to be a bunch of different types that I'm going to need to define here for this to work. First one's just going to be a program. So it's going to have a couple different things. It's going to have a global scope. I guess it's, do I want to give it a name here? Or is that something I want to do later? We'll worry about that later. What else needs a... what does it need? What does it need? Maybe modules? Like a list of modules? What else? I guess result. So if it attempts to evaluate this and fails, it'll spit out a result. Okay, so we need to define a scope for this. So struct scope. Now this is going to contain all the variables. Oh, we also need types, because I don't necessarily want to allow for types to be defined in a particular scope. I don't know, actually, types being defined at very particular scopes actually could be useful. Okay, yeah, we'll just do that. So variables, functions, and types. All right, all those are going to be defined at various scopes. So global scope is obviously going to be the most common place for functions and types to be defined, but you'll obviously do have global variables, and there are instances where you're going to have local functions and or types. So like this is a thing in a lot of languages, lambda functions. That is an example of a locally defined function that I guess can break out depending on the language, but generally speaking, it doesn't. Anyway, all right. Okay. All right. Oh, thank you. Okay, so that's going to return an error function, or sorry, not error function, an error code. And so let's have print. And all of these, I think, can just be constant, because I'm not planning to place pointer. Okay. All right, what else? Okay. Good, real quick. So let's go global. And this is going to there. Struct scope parent. This should be pointer. So in any given scope, you want to be able to reference the parent scope. Otherwise, you won't be able to detect when someone is trying to reference a global variable inside of a inside another scope, or I guess a parent variable, not necessarily just globals. Okay. Let's try. Need to define some things. So let's try defining a function. So we're going to have a name. It's going to have a return type. It's going to have a list of arguments. I'm going to put that into parentheses there. So functions. Actually, for now, I'm just going to get that one function. Okay. And there's going to be a whole bunch of other stuff that's going to need to go in there. And it's going to need its own scope. So let's call it a body. Okay, so scope's going to need to be defined. So maybe, I guess, scope might be defined at the very top. And then do something like this. Type def. Just replace it with func. And same kind of deal here. I think type can be defined here. So it's going to need to have so we call those components, maybe? These are going to be like subtypes, because most types nowadays are defined in terms of other types. And the one exception to that would be primitives, right? Primitives are not defined in terms of any other subtypes. But like if I wanted to define a type of error, then it might have something like a subtype of error code, and it might have a subtype of error message, and things like that. So it definitely needs those. And then the number of types. So type, let's call it component count, something like that. Let's include cd h. Okay. Okay. This is a bit. Okay. Huh. It's also going to need alignment, and that's probably going to end up being something like int. So alignment, you don't know, types have a certain size, right? And so, like, let's say you got a char, a char. That's typically a 1 byte type, and so its alignment is 1 byte. When you start talking about composite types, the alignment is the minimum, or sorry, the maximum alignment of all of its components. So if you've got a char and an int, typically an int is 4 bytes in width. It's got a 4 byte alignment. And so your type overall with all those components will be 4 byte alignment. Which, depending on how things are organized, if they're organized in sort of a naive order, you could end up with something a bit problematic. Like, let's say we want to do struct like this, and I can just throw this into comments because I don't want to have to do that. Okay. Let's say we've got char code, and then int thing1, I don't know, and then Boolean, the Boolean isn't necessarily defined by default in C, but we'll pretend we're using stdbool or something. And then we'll call it condition, and then long thing2, right? And now, if all this was kept in order, because of how CPUs like to do alignment, you would end up having to pad these in order for this to work. So this char here would probably be padded with something like 3 extra bytes to make up for the fact that it's just 1 byte, and then it's right next to this integer. So this would be padded with 3 extra bytes. This int here takes up 4 bytes. So already we're using 8 bytes when we're only supposed to be using 5, which isn't necessarily a huge problem until we start looking at this. So this Boolean is going to also be 1 byte, because technically speaking, a Boolean could be represented by a single bit of information. So already, kind of an issue, but that's, we'll set that aside, pretend that's not a problem. It's still 1 byte, but this is already has 4 byte alignment because of this integer. So normally, even if we exclude this long here, we pretend that doesn't exist, this would still be an extra 3 bytes of padding in order to make all of this fit properly and align properly. So that's a thing, right? And longs, now depending on what CPU and architecture you're running on, this might be 4 bytes, it might be it might be 8 bytes, or it might be only 4 bytes. We'll pretend it's 8 bytes. So this 8 bytes here isn't aligned, and if I'm not mistaken, this would basically cause this entire struct's alignment to shift up to 8 bytes. And so in order for this to fit properly, I'm pretty sure you would end up having actually 7 bytes of padding. So what could have been 16 bytes of data, so like this is the really naive partition scheme, or not partition, padding scheme. We'll just call this one good example and bad example. In 1 moment. Okay, so bad example. Good example would probably be something more like this. So we would have long thing2 up here at the top, because it's the thing with the highest alignment requirement. And then we have int thing1 right there. And then code could go at the bottom, and condition, or code could go next, and then condition at the bottom. So what ends up happening is these will be kind of compressed more effectively here, because this long here is going to be aligned with 8 bytes. Then this int, because 8 bytes is already divisible by 4, this int is going to be able to be aligned here properly. And then this code here, again, it's 1 byte, and 1 is, or 4 is divisible by 1, so this doesn't need padding. And then this condition, again, 1 byte, so it doesn't need padding either. And then the only padding you would probably need would be these two, because 4 plus 1 plus 1 is 6, so add on 2, and you've got it aligned by 8 bytes, and then you can just add in, more structures after that. So this up here, this is 1, 2, 3, 4, 8, 16, 24 bytes. Sorry, 24 bits, my bad. No, it's 24 bytes. I'm losing my mind. Whereas this, should have said byte, excuse me. So 8 bytes, 4, 6, or sorry, 4, 5, 6. So that's going to be 14 plus 2 for padding. So this is 16. And these are relatively small structures. You can imagine things get a little more, can be quite a problem if this sort of alignment scheme isn't properly handled. So yeah, alignment matters. And there's actually an even better way to do this depending on what you're trying to do. So for example, let's say we wanted to make an array, right? Let's say we wanted to make a struct good array example, right? What we could do instead of this, because if we do an array, then this padding is always going to need to exist, right? So we're always going to be losing 2 bytes of data, right? Or 2 bytes of space. And that won't matter in a small setting where you're using like, you know, like less than a kilobyte of RAM. It's not probably going to be a huge issue, obviously, unless you're like on an embedded system or something. But if we want to really save space, then what we could do, instead of having an array of this good example structure, which would cause us to lose 2 bytes for every 16 bytes, we could instead have whoopsies, array, and then I'm just going to go ahead and copy there. Okay. For that there. And we'll pretend whatever integers is there. So, right, so it's you know, an array of arbitrary length, right? So what is going to happen here is, you know, we say we put in, I don't know, 19 values, excuse me. Okay, so now the alignment here is, we're going to be saving space because, first of all, this long here is always going to be aligned because it's 8 bytes. This integer, so like this is going to I think I need to actually put in some numbers to this. So we'll pretend this is starting at memory address 0. This is not at all what would normally happen, but you know, whatever. 0x and then 19. Shoot, I chose a number that I can't quickly convert in my head. Oh gosh, 16 would be what? That's, I think it would be something like, I think, not 19, 3. That would be represented as 13. Like 13 in hex, right? Not 13 in decimal. Yeah, because 16 minus 19 is 3. Okay, yeah. So that would be right. This should be 0. This would be 13. And then no, it wouldn't. Because that'd be times 8. Shoot. 152 divided by so this would be 9. 8. I think that's correct. I think I've got the numbering right here. Okay. Whoops. Okay. Then, so 152 plus 4 times 19 is 228. Divided by 16, that's 14. So, let's see, 14 is E. And then 14 times 16, that's 4. And then this would be, let's see, I don't recall if alignment needs to be divisible by 8 just in general. I don't think it does. I think we're fine with this. I don't recall if that's a requirement. If it is, then you know, that is what it is. But anyway, we'll pretend that it is for the sake of this, just so that it's not I'm not offering like an unfair advantage essentially to that particular, like to this sort of test. Okay, so let's see, 14 times 16 plus 8. Okay, so 232 plus, in this case, this is each of the chars is 1 byte, so plus 19 divided by 16, that's going to be 15. So that's going to be F, and then times 16, that's going to be 11. 11 is B, if I'm not mistaken. So FB, that's the starting point. So actually, I should probably put the start and end. And then 0x0 E8, 0x00, oops, FB. Okay, now this one is going to, let's see, FB. So that's going to go to, I think that's correct. Right, plus 15 times 16, yeah, 250. Yeah, 251. So if we round that up, so for alignment's sake, which I think is what you're supposed to do, quick, let's do 4 byte padding, that, and then 19, 24, so I think that's another 5 bytes of padding. And then same here, it's going to be another 5 bytes of padding. So this would actually be 1, 0, 0. And then 19, it's going to be 3 there, but because, again, this is padding to 8 bytes, so we'll do that. 5 byte padding. Okay, so we're getting a total of 14 bytes of padding with this sort of, example. Now, compare that to if we were to use even the good example here of like a well-organized structure with, proper alignment, we would lose we would end up with 2 bytes of padding per member of the array. So if we were to do 2 times 19, that's 38 bytes that we're losing, as opposed to 14, which is a, what's it? So that's like a 270-ish% increase compared to if we were to use this good example. Thinking of it another way, what was it? It was like 38 minus 14 divided by 38. That is was a 63% decrease in the amount of padding. Right, so you're saving a decent amount of space. It's not saving a ton, but 38 bytes is not nothing. And in the case of the bad example, let's pretend we were using the bad example, right? That one is 24 bytes in total, and of those, what is that? That's not 12. That's 10 bytes of padding. So 10 bytes of padding, already we're getting 190 bytes of padding. Right, so 190 is, yes, it's like 600%. It's 5 times the amount of padding that you're using with this one, and no extra data is being stored, right? This is just entirely waste. And if we compare it to this example where we're using, first of all, this is it's not quite the worst, but it's almost the worst one. The worst number here would be something like 17, or yeah, 17, because that would mean that this padding here would need to be increased This one would be the same because it's an odd number still. If it were an even number, then this would go away. This stuff would be 7 bytes of padding. So the worst case scenario for this, we're still only getting, that's going to be 18 bytes of padding, right? As opposed to 38 here, or not 38. This would be scaling depending on the size of the array. And that's the other thing. The padding that you get here scales based on the array. This one is just based on the divisibility. So if you get a number that is particularly divisible, then you will end up with less padding. This one scales with the size of the array. This one really scales with the size of the array. So alignment is important, and you can save yourself a lot of space and also just time, because if you need to allocate space, you need more available, and if you want to allocate, it's just bad. You don't want to take up extra space, especially when you don't need to, because you aren't getting anything by doing this. You lose nothing by optimizing it like this, and you lose, the only thing that's really the problem here is that this is more complicated and requires a bit more setup. But there are ways around that even. So the one major downside, I guess, would be that it's a bit more computationally difficult just in principle, but depending on how you're working with this, it may work just fine. So anyway, fun, interesting stuff. Okay. So that's all that to say. Alignment, that's going to need to be tracked for a type. Okay. What stuff? Okay. What I need to do. Yeah, so we're going a little bit over here. I think I'm probably going to go ahead and end the stream here, and then I'll try to continue streaming tomorrow and continue doing this in the future. Kind of got thrown off the track for a little while there, but hopefully I'll be able to continue streaming. So anyways, thank you all very much for watching, and I hope you enjoyed and found it interesting, entertaining, and I'll see you